little bit about our speaker for today. Praga is actually one of my teammates in ALECA. She's graduated from Curtin University in year 2019, and she's the reservoir engineer at ALECA for 1 year. And she's one of the research and developed technical modules for ALECA system. And she's a huge animal lover, especially her cats, right? Okay, so I think we can start now because it's already 2:05 p.m. And Praga, the floor is yours.
Okay, thank you, Eza. Good evening, everyone, and hope you are all safe. The COVID cases are through the roof now, so please follow all your SOPs and be safe. Just out of curiosity, is there anyone logging in from a quarantine center? Yes, no, Eza? Is there anyone logging in from a quarantine center?
Yeah, is any one of you? No. Stephanie, Albert, and Ziad say no. Thank God. So I hope everyone is safe, and healthy.
Yeah, happy that everyone is good. So first of all, I would like to thank all of you for being here. My topic for today is production forecast and recovery factor. I know it's a technical topic and it can be very dry presentation, but I will try my level best to keep you engaged, all right? So I will first cover the production forecast and then followed by the recovery factor. Let's start. To begin with, you saw the tagline on my poster, right? Marriage made in heaven. How about reservoir engineering and geology? What do you think of its meaning?
Anyone? Anyone would like to share your feedback on the marriage? Peas and carrots. Oh, Mr. Such is difficult. Yeah, I agree. Marriage is difficult. But maybe Praga can explain. It's very easy.
Okay, what is a marriage? I'm sure everyone may have different views, right? Especially the ones who are married for some time now definitely have a different view. Like Mr. Sir just now, he may not have a very happy definition towards marriage, I guess. But I'm still not married. So in my opinion, marriage is a collaboration between two people. Yes, it's a collaboration between two people as one family institution. Likewise, I feel that in order to make a decision that focuses on value, professionals from reservoir engineering and geoscience must collaborate as one. And today, I suggest ALECA to be a platform for you to do so. Geologists, they work on characterization of the reservoir and geomodeling, right? They estimate the in-place volume of the reservoir. They do a lot of analysis and provide parameters, the numbers for reservoir engineers to use to find the reservoir performance. And what do REs do? We do the math, we do the simulation, we work on the numbers and find solution on how we can maximize the production. Our goal is the same, to get the maximum out of the reservoir. But why don't we communicate? Why do we still work in silo? That is why you are here. Today, I intend to get you to at least think about tying a reservoir engineer's math to a geology's in-place estimation using recovery factor as a piece of collaboration, okay, to perform a marriage. I'm sure for those who've attended our previous talk may be familiar with this chart. Yes, it's the 5 main disciplines that we have on our system, ALECA. So we have the main 5 disciplines: project management, hydrocarbon initially in place, HCIIP, production forecast, economics, and sustainability. There are several modules under each of these disciplines and they are linked to allow collaboration across the disciplines. My focus today would be on HCIIP and production forecast. My aim of this presentation is to show decline curve analysis for production forecast, to show recovery factor as a point for collaboration between reservoir engineering and geology. And of course, I am going to share demo on how ALECA as a cloud-based toolkit can help you. Let's go into the topic with production forecast. Decline curve analysis. DCA. Well, the reservoir engineers would be familiar with this term, but it may be something new for our friends from geoscience here, right? I actually asked my colleague Yasmin, who's a geologist, whether she learned about DCA during her course of study or during an internship. She said no, and she also said commonly geologists may not know about this, so I hope this can be a brief introduction for you. So, what is DCA? DCA is a graphical procedure we do to forecast production rate and expected ultimate recoverable reserves. The concept of DCA is to extrapolate trends in production data from oil and gas wells. DCA is commonly conducted on plots, production rate against time and cumulative production against time. This method actually analyzed the decline in production rate. So production rate declines as a function of time, loss of reservoir pressure, and changing relative volumes of produced fluids. We have three types of decline curve, namely exponential, hyperbolic, and harmonic. Exponential would be the common type you see in conventional oil and gas well, and it is considered as a conservative approach, a traditional approach. Hyperbolic, it is common in less permeable and tightly formed reservoir, and of course harmonic, it is often seen in new shale horizontal wells, and it is considered as an optimistic approach. The term B here is a decline exponent, which is dimensionless. The value of B factor for exponential and harmonic is fixed. It's 0 and 1 respectively. You can only adjust the value when we use hyperbolic. In simple words, we can say B factor is the one controls the steepness of the graph or how harsh the decline would be. We can note that in the harmonic curve here, okay, the B factor equals to 1. So it has a dominant effect on the shape of the curve. It maintains the shape of the curve to be flat, and when the B factor is equals to 0, you can see the opposite. The decline is quite harsh. It's very steep. So B factor changes with flow regimes. The best way to find B factor is through learning curve and analogy. Now that I know I have to use DCA from do DCA from production data, how would I use production data to do a forecast? Let's start with brownfield. We can learn from the existing production data on what the trend of the curve and parameters like annual decline rate and B factor was, and we can assume the same when we do the forecast, right? Okay, let me zoom in this graph for a clearer view. Okay, here you can see QI is your initial rate, which we can normally get from experts report we have on the reservoir, right? Then by fitting curve in the existing production data, which is the green curve over here, we can learn the DI, annual decline rate, as well as B factor, the decline exponent. So as you can see, we fitted three curves here, which indicates minimum, most likely, and maximum for us to get a range for input parameters. So if you're forecasting from this data, you can pick a point towards the end of the production, and you can have a range of values for your parameter input. So this is for brownfield. I have a question for you. How about greenfield? How if you don't have a existing production data? What do we do?
Yeah, again, the question is, how about greenfield, right, Praga?
Yeah.
On the floor, if you, Yasmin said refer next to. Sharina said analog. Mr. Gordon, yeah, analog. The field next door.
Okay, thank you everyone. Yes, analog. And yeah, I was expecting Gordon to say analog, and I'm pretty sure he's smiling because he's an analog guru. Right? Okay, so the basic critical element for analog is consistency for all technical parameter. So how do we define analog reservoir? According to PRMS, the analog reservoir is defined as reservoir having similar rock and fluid properties, reservoir condition, and drive mechanism as the reservoir of interest. So typically reservoir in the same geographic area and of the same age would provide better analog. You can relate it like when we move to a new place, the first thing we check out is our neighbors, right? So when you study a new green field, check out your neighbors first, okay, neighboring fields. Analog fields, however, are typically at more advanced stage of development than the reservoir of interest. Of course, we want an analog field like that so that we can use the production data and learn from it. The properties that we can often compare between analog reservoir and the reservoir of interest are reservoir lithology, trap mechanism, basin type, depositional environment, reservoir properties, and structural setting. Okay, here we come for the demo of DCA tool on ALECA. So I'll be showing you ALECA platform, but I'll be turning a little bit towards my screen here as I have it here. Okay, hope you can bear it with me. Let's go. Okay, can you see ALECA? Okay, I hope yes. Okay, welcome to ALECA. This is our ALECA module, DCA Forecast Probabilistic. The aim of the module is to analyze declining production rate and forecast future performance of oil and gas wells. So here, this module, it does calculation deterministically and probabilistically. I will walk you through this module and also walk you through the inputs. So when we click edit button, you go to your input page. You can choose your hydrocarbon type, whether you want oil or gas. I'm going with oil. And then you can input your start and end date. So this would be the duration or the period of forecast. And you can choose increment. You have 5 types of increment choice. It's either daily, monthly, quarterly, calendar annual, or corporate annual. I'm going with quarterly today. You can input your downtime and your number of increment will be calculated automatically. Let's go for your input parameters. Your input parameters would be initial rate. You can choose the unit, annual decline rate, terminal decline rate. Terminal decline rate is not applicable to this demo as this parameter is commonly used in unconventional wells. Plateau, you can indicate how many of your increments would be in your plateau region. Abandonment rate, and of course B factor. And here you can choose which type of curve you want to use for your forecasting, either exponential, hyperbolic, or harmonic. Okay. As I said, this module does calculation probabilistically as well. So you have to pick your distribution type. You can choose from triangular, uniform, or Swanson's. I'm picking uniform for today. And then dependency. You can set dependency where you can set dependency of one parameter with another parameter or inverse of another parameter. To keep it simple, I'm going for all independent today. You are required to put in a range of input, minimum, most likely, and maximum. Then you hit lock. So here I've already run it for you to make things easy. But you can hit here get 100,000 runs to initiate the calculation. Okay, so we have our deterministic calculation here, this section, and the probabilistic calculation in this section where you get your P90, P50, and P10. Well, you get your ultimate recovery till abandonment rate here based on your abandonment rate input, and 4 results for your forecasting. So to begin with, you would get rate at start of increment. This is the graphical representation of this result. So if you can see, rate at start of increment here is an instantaneous number. It's on the first day of that particular increment. Then you have average rate for increment. For example, within the increment, you have 15 days. You would have the average rate would be an average for the 15 days. Hence, it's represented by bar chart. That's for flow rates. How about cumulative production? For cumulative production, again, it's an instantaneous number on the first day of the increment. And you can also get production per increment, meaning total production in that one particular increment. All right. So this graph section, it's actually interactive. If you feel it's too much to see, you can easily shut off. Let's say if you want to just view your P90, P50 and P10, you can easily shut off the others and do your screening. All right. Then remember we chose the distribution type, right? We want to see how our input parameters got distributed. You can view it through this chart. You can choose your parameters and see how the distribution curve worked. That's for DCA forecasting. Forgot to mention that you can also refer the equations here that we use behind this module. Okay. Coming back to my presentation slide. Okay, I have a question for you. If you see on the curve here, let me zoom in for you. Okay, if you can see, our B factor values here are different. We have the minimum 0.03, almost close to 0, and we have 0.99, almost close to 1 as maximum. But if you see the curve, there is no much change in the shape of curve. What do you think it's causing this to happen? Anyone?
Yeah, on the first, it's too short of a time. Praga, can you maybe like zoom out a little bit?
Okay.
Yeah. So the question was, there's not much changes on the curve, right? So what do you think happened due to this incident? So Mr. Sitch, too short of a time, within only a year. Anyone else on the floor? Okay, I think you can continue, Praga.
Okay, thank you, Eza. Yes, that was a correct answer. The period of forecast. When the period of forecast is a short term, the shape of the curve is not largely affected by the B factor, but in long term, definitely the shape will be affected. If you notice, the demo just now is only for 4 quarters, right? It's only for a year. So no much effect of B factor on that. But if you forecast for maybe more than 3 to 5 years, you can definitely see the difference. All right. Now, let's move to the recovery factor, the point for collaboration. Okay, first thing first, what is recovery factor? Recoverable amount of hydrocarbon initially in place, and it is normally expressed as percentage. The recovery factor is a function of initial and abandonment pressure and also depends on drive mechanism. Why do I say recovery factor is a point of collaboration? I have put in a very simple equation. Recovery factor equals to cumulative hydrocarbon. Who give cumulative hydrocarbon? Reservoir engineers, right? We have it in the DCA. Divided by HCIIP, the number from our geologists. So this is why I say recovery factor would be a point of collaboration. Okay. Question again. What do you think the typical recovery factor is for oil and gas?
What is a typical recovery factor in oil and gas?
For oil and gas.
For oil and gas. Okay, maybe we have some, depends on a lot of factors, and some say oil will be 30%, gas will be 60%. Farida said 50%, and Mr. Gordon said he need more data. Albert 20% for oil and 60% for gas. Yeah, I think about the similar number, that 10 to 30% for oil and 60 to 80 for gas.
Okay, thank you everyone for answering. Yes, everyone is about the range. For oil, the typical recovery factor is within 25 to 30%, and for gas, of course, it's higher, 50 to 70% on average. So why do you think the recovery factor range for oil and gas differs this much? So typically for oil reservoir, our recovery factor is low, mainly due to residual oil saturation. When we start depleting, we must make sure the reservoir pressure does not drop much, certainly not below the bubble point pressure, else the oil won't move. You will only have gas coming out from the oil and losing the energy of the reservoir. Recovery factor for oil depends on complex interplay between geological, physical and economic elements. How about gas? Why is the recovery factor of gas is high? The key for gas recovery factor is gas expansion factor, which is also a dimensionless parameter. As reservoir pressure reduces, the gas will keep expanding, and even gas that are trapped on residual oil will eventually escape around the edges, leading to high recovery factor. The typical gas expansion value is about 200. Also, gas have lower viscosity than oil. So, where gas can flow through low permeability rocks that may not flow oil. But when pressure drops to a very reduced level, the expansion factor can also reduce to be very low. Then that is an issue. Or too low pressure, reservoir pressure causes the surface rate to be very low, that it is no more profitable. Now that is an economic limit, meaning we are reaching the abandonment pressure. In this case, you can increase the recovery factor by installing compression equipments on surface. Okay, so like I said, recovery factor is a marriage, right? So how is this marriage done on ALECA? Let's see. Okay. Recovery factor matrix. As you can see, our recovery factor matrix has DCA forecast parameters and also HCIIP parameters. So for DCA forecast parameter, you can choose whether to use ultimate recovery till abandonment rate based on your abandonment rate input, or the cumulative production till end date, because sometime even at the end of increment, you may not have reached the abandonment rate. Okay? And then you can input your cumulative production, existing cumulative production. For HCIIP parameters, for this recovery factor matrix, in order to connect, the HCIIP module must be pre-filled. So our geologists would have filled the HCIIP module here, and for example, they've created like 10 zones. All the zones will be listed here, along with the option of roll-up tools. So you can either calculate recovery factor for individual zones, or you can use roll-up tool to do it for all the zones listed. All right, I'll choose zone 1 for today. And within a click of a button, you can link these two modules and import your STOIP from HCIIP module here. HCIIP module also does calculation deterministically and probabilistically. So you have your deterministic STOIP and your simulation result STOIP here. And automatically recovery factor for your existing production and recovery factor for your forecast will be calculated. Yes, that's a lot of numbers and it may be unclear here. So I'll switch back to my slides to give you a better view. So here we go, recovery factor matrix. So here, if you see, always we focus on our P10, P50 and P90, right? For a quick screening, you can see our P90 here, it's about 33.38% and your P10 is about 26.49%. So it is within the range, isn't it? So we are good to go. For instance, when you are doing screening like this, when you check your recovery factor and you come across very low or very high recovery factor, we know it's a red flag. At that time, both the geologists and reservoir engineers can be updated with the red flag, and the geologist may want to revisit your HCIIP. On ALECA, the projects are connected. So when a geologist update the HCIIP module, the update will be reflected on all the other modules as well. So with the click of a button, you can sync and update your projects. These are my references that I used to make this material. And before I end, All the reservoir engineers and geologists should start thinking about collaborating on a platform. This will save time and of course cost in making decisions that focus on value. Normally we don't understand each other's language. Like when a reservoir engineer use technical term to talk to geologists, they don't understand it, and vice versa. When geos start talking with geological term, reservoir engineers go blank. So we don't need to necessarily know in detail, but at least we need to have an idea about other disciplines, and ALECA can be your platform to collaborate. With ALECA, as I mentioned, the instant updates that reflect changes on project saves time and information transfer and reduces the communication gap. Let's start thinking about this. Let's break the barrier or the silos and start collaboration. With that, I end my presentation for today. I would like to again thank all of the participants for joining and of course staying till the end. I truly appreciate it. Thank you.
All right, thank you, Praga. That was a very great presentation, very clear and understanding from everyone, I hope so. Anyone from the floor, do you guys have any questions that you guys want to ask Praga? Please drop your questions below in the chat box. And really good job. Yeah, Mr. Gordon said really good job. I personally think she's our best presenter in ALECA, to be honest. So if you guys have any questions, please drop the feedbacks or comments or questions about ALECA system, about the topic today, and we will attend before we actually end the session for today. Okay, so Praga, do you have any reference papers on the RF or the recovery factor?
Yes, I do. We can
maybe you can share.
I don't have it on the presentation slide now. Maybe you can see the reference here, but if you want, you can drop your email in the chat box and I'll send you the reference paper, the link to the reference papers.
Okay, great. Okay, and then Mr. Gordon, if a recovery factor is low, what are the possible reasons, Praga?
Recovery factor is low. It could be due to the aerial extent. Sorry?
Continue, sorry.
Okay, recovery factor, first thing, it depends on the drive mechanism in the reservoir. Other than that, like I said, if it's a low recovery factor in the recovery factor matrix, it's a red flag, right? We may want to revisit our HCIIP module, the HCIIP estimate, and also again work on our DCA forecast.
All right. Great. I think we're going to wait. Number of, Mrs. Sitch, number of wells.
Number of wells.
Okay, can we have more longer elaboration of the questions? Economic limit on the number of wells.
Economic limit on the number of wells. Okay, the recovery factor. Oh, okay, maybe we can link that. The recovery factor may depend on the economic limits. For example, if you feel your reservoir has more potential, maybe you need, for example, as I mentioned before, when the recovery factor of gas is reduced at surface level where the gas rate is too low to be profitable, then it's an economic limit, right? Now it's your job to convince your management to put a compression tool up there. But of course, it depends on your economist. So maybe we need another session on how to marry the economist.
Yeah, okay. So I think we can end this session, but before that we would like to actually remind you guys again that we have the talk next week on the hot seat of carbon tax, carrot or stick. Again, thank you so much, Praga, for the great presentation.